The purpose of this video is to highlight the seamless flow of Integrated Systems Diagnostics Design data through the design development cycle. We will be demonstrating a snapshot of this capability using the QAS that transmits RF data in 4 quadrants and receives RF echo data from these quadrants and decodes them into 6 RF complex data outputs. The system utilizes redundant transmitter-receiver elements to demonstrate how the fault tree presents redundancy and the resulting failure rates. We begin by describing the QAS subsystems as contained in a higher systems level view. These subsystems represent hierarchical containers of lower level assemblies and components and all of their functional interrelationships. Let's first descend into the QAS transmitter-receiver assembly. Once inside, we notice that we have captured the functional interrelationships of these components. Included are feedback of outputs for built-in tests to provide isolation capabilities. This capture will reflect any interim development as the design progresses, and ultimately as the design is delivered and kept throughout the sustainment lifecycle, offering full product lifecycle traceability. Now let's reuse any of the reliability data as available in the QAS engineering database. This is performed by a spreadsheet import into the design capturing paradigm. Failure modes, failure effects, severity, and any other relevant data can be immediately imported into the design or re-imported as the design or data changes. Once imported, we can observe the imported data as it instantly corresponds to each of the component properties in these panels. And also, we can view this data as it interrelates to the associated objects in a grid-like view. Notice that this data is represented for each component and by mission phase. Now we'll go back to the subsystem design view so we can generate some turnkey assessments. We will only demonstrate the basic procedure, but we should note that these assessments are exhaustive and offer unmatched interdisciplinary cross-validation capabilities during the design development process. We will first reorganize and restructure the QAS transmitter-receiver assembly database, but also include any new changes made anywhere in the captured design data. At the same time, we'll be calculating the current diagnostic implications and its interdependent diagnostic strategy to support our sustainment objectives. This takes about a couple seconds to recalculate. At this point, the diagnostic integrity of our design is determined to have a fault detection of about 100% to one component, and we can isolate to a fault group of one component 78.64% of the time. At any time, we can view or interactively insert faults into our diagnostic flow tree in this panel on the left to see the diagnostic sequence determined to best isolate any failure based upon our sustainment criterion. Notice that the selection on the fault group in the diagnostic flow tree interactively highlighted the failed components in our captured design view. Let's save this design, and then we'll reuse this design data to generate a turnkey FMECA for this QAS transmitter-receiver subsystem. We'll quickly mention that the columns of data desired to be used in the FMECA can be extensive, and when we settle on a specific template, we're able to reselect and reuse that FMECA template at any time in the future to maintain full consistency. We can include diagnostic and root cause details in our design specification FMECA just as seamlessly, when desired. Moments later, we have the FMECA for the QAS transmitter-receiver subsystem as cross-validated with the diagnostics. In this FTA of the QAS transmitter-receiver, for example, the probability of occurrence of the loss of communications critical event, identified by the Q number, is listed here. In this example, the probability of experiencing this critical event also takes into consideration that this level of criticality exists for a mission length of 1 hour. Stepping back for a moment, we can notice that the blue circles describe the lower level component primary critical failures carried from the integrated FMECA. Here we can observe the combining of lower level critical failures within the FTA structure that led to the occurrence of that specific critical event. Now let's look at the switch matrix subsystem. We will note that the redundant transmitter receivers are interrelated in the proper functioning of this switch matrix subsystem, which is why we must always consider the interdependence of the functions and failure effects of each subsystem when we design for assessing the design's diagnostic integrity for delivery, and at the same time for the sustainment lifecycle. As you can see, here is the lower level model of the relay matrix. Like before, we can auto-generate a FMECA, and likewise its associated FTA architecture, depicting the switch control primary failures and its propagation path to the loss of Q1 control. An interesting note here: although 100% can be detected, only 25.97% can be uniquely isolated based on the diagnostic integrity of this design. At last, revisiting the QAS's system-level design and following the same assessment product script, we're able to immediately generate a system-level FMECA and its companion FTA, just like we're able to perform for any integrated subsystem. It's clear now that the loss of QAS transmitter outputs would occur with the loss of the redundant transmitters. Finally, this diagnostic database is immediately transferable and reusable in a runtime sustainment implementation. Please be sure to view other videos describing additional advanced capabilities from DSI's Integrated Systems Diagnostics Design video library.